You old timers know what it is. It's a tuned circuit, calibrated tuned circuit. It's a capacitor, coil, and light bulb in series. I've got another one here and I'll be demonstrating it. But when I got into amateur radio, that was called a frequency counter. Okay? And frequency counters didn't come along until vacuum tube frequency counters, which started to show up in the early 60s. Some of them showed up a little earlier than that. Then finally they became solid state. But before the frequency counter, all they could use was a test oscillator calibrated against a wave meter. And that was the frequency standard. Back in those days, amateur radio operators didn't, before in the early days, in the teens and the 20s and the 30s, didn't talk much about frequency. They talked about wavelength. Maybe on 40 meters or 39 meters or something like that, because they didn't have a good way of measuring frequency, but they could measure wavelength. And this was how they did it. Only they measured, it was calibrated in wavelength. The other thing I'm passing around here really fast is the Quartz Crystal. In the early days, all the amateur radio transmitters were controlled by just a coil and capacitor for frequency. They drifted around. You didn't know exactly where they were. The first 40-meter coast-to-coast contact was made in the vicinity, quote-unquote, of 40 meters. You know, somewhere in there. And so what happened was in the middle 20s, somebody discovered you could apply quartz crystal to controlling frequency of oscillators and make an oscillator oscillate on a desired frequency. And so all the transmitters became crystal controlled. And of course that was taken to a high art of development. But I've got a couple of crystals here and I'll show you an illustration. This one is for a color burst for early TV set was 3579 kilocycles, and this one here is a World War II surplus on 7010. And I'm going to pass these around, and you can check them out. And let's see. Oh, I got a quick question. Anybody got a small screwdriver? Anybody got a screwdriver at all? A Boy Scout knife or something?
What, you just need one?
No, okay.
You're gonna steal one?
Small. Let's see. Which one is a screwdriver?
Mashed potatoes. Somewhere in there, there's a screwdriver.
Oh, there it is. All right, I found it already. I just have to hook up a couple of wires here. This is all homebrew equipment, and I don't really have much commercial equipment. So to do this particular experiment here, I had to resort to using homebrew, and I got to hook up this power supply really fast here, and
Who's waiting for Michael J. Fox to show up right now?
yeah.
I'm waiting for the spark.
Oh wow!
I cracked myself up. Yeah, like everybody else around.
Well, that blade is too thick.
You want a Boy Scout knife?
Yeah.
Try a dime.
Wait a minute, maybe I got it. Oh yeah, that'll work better. It's just the blade and the other one's too thick. Yeah, 12. Boy, I don't have any left over. 12 is in my body.
That's all we have.
A Come on, you can get on there. Well, there it is. I believe.
I wonder what's happened to my old.
Well, what these guys are working on now, they're
Yeah, I got it now.
they're not.
All
Calling
right. Don't take a very
like.
long time. It's all flashed together.
They kinda had it down. So they drew it a little bit.
Maybe use that for the other one. Thank God the demonstration doesn't take long. Anyway. I want to put an SWR bridge in here. One of the things I want to point out is at the point where people were building this kind of radio equipment, there was no such thing as an SWR bridge. That came along later. And we had other ways of determining that we had a good match. And
Three commas.
all right. Yeah. Bill, did you bring your tube?
I forgot it.
Oh. Well, let's see. Maybe we're all right anyway.
Junior rig by that light. Remember those days?
My dad used to do that all the time. He'd be in.
Well, it's good while it's still dry.
Yeah.
Antenna.
So interesting.
I guess you're all wondering why I called you here today.
Anyway, let's see. I'll just have to set this here for now.
You want me to hold that
Okay.
up or something?
Yeah. Well, should be.
Oh, this wire.
Where did it go?
How would you say
Hold my beer while I flip the switch.
I remember those days too.
And I'm only got 6.
Did you ever get an RF burn?
My dad had burns on over 90% of his body.
Really?
Yeah, he worked with Dr. Van Allen.
What frequency are you on?
Wow.
Hold on a minute. Hold on, 7 minutes.
It was a program, Phill. Wavelength.
Approximately 49.
Seven
You
seconds.
can't find it?
7 minutes. 7 minutes.
Great.
I've got it.
Tubes are heating up.
I must have another electric.
You used to let it after 5 minutes or 10 minutes.
Letter T.
I've heard that too.
I know the code, it's a letter T.
Zero beat.
They're not listed on now.
Okay. Alright, this is our antenna, okay? And this thing over here
I get
is an antenna coupler.
Does the volume control work on that radio?
And Let's see. Can you put the schematics up there really fast?
Which one do you want, sir?
Put the first one up there.
The one that's numbered number 1?
Yes.
Good start.
All right. Anyway, I'll do a little explaining here. First of all, this is a homebrew transmitter of one of many I built. Use a pair of 807s and whatnot. This runs ordinarily about 50 watts, but I use a different supply for the oscillator and everything than I use for the amplifier. So I've got 2 power supplies here. And this is a boiled down circuit of this transmitter with a bunch of stuff left out. But actually, this transmitter would work with triodes. The only thing that's missing in this circuit is a neutralization capacitor that would come down to the bottom of this coil here from the grid, or from the plate over there. That's the only thing that's missing. I left it out. But basically, yeah, okay. Oh, wow. All right, so I want to explain this a little bit to you because it would help you to understand not only vacuum tube electrons, but radio and or communication in general, because inside every radio you got, it boils down to a circuit almost this simple. And you got over here, this part here, the crystal, a resistor, tube, variable capacitor, coil, is an oscillator circuit. And what does an oscillator circuit do? It generates a sinusoidal RF signal, wave. It's an electric voltage that varies in time sinusoidally. And this oscillator, this crystal, controls that frequency because it's oscillating itself, and it's in the little holder, and it's oscillating back and forth like this, almost like a drum head would oscillate. It's the same oscillation, the Bessel's function. And the thickness of the crystal and the size determine what frequency it oscillates on. And the crystal's made out of quartz. And when you put a voltage on quartz, it bends the quartz. Or if you bend the quartz, you get a voltage. And that's called the piezo effect. And so they're using, in this case, this transmitter would date from about 1927, and they were using a crystal to control the frequency as opposed to having a tuned circuit in here like this over here. They had a crystal instead. And this is a grid leak. It allows there's a voltage coupled to this crystal through the grid to plate capacitance of this tube here. It's like an invisible capacitor in here. And some of the energy in the plate circuit that gets amplified is fed back to the oscillator and makes the crystal oscillate. It generates a voltage that goes on the grid, and that voltage on the grid controls the plate current, and the plate current changes and induces oscillation in this tank circuit here. Some of that energy is fed back to the crystal, and the process repeats, and that's how an oscillator works. Then you get over here, you got this tank circuit here. They call them a tank circuit. And you know, that's one reason, one thing I'm not sure I understand why they called it a tank circuit, but actually it's holding energy. So that's an old term that came from long, long ago.
Holding energy.
And we get capacity, we couple the voltage across this oscillating tank circuit into the grid of the final amplifier, and it makes the voltage go up and down on the grid of the amplifier and controls the amount of current that flows across from the cathode that emits electrons to the plate that collects them. And those electrons flow through the circuit down to our B+ supply through this meter here that measures the amount of current flowing in this plate circuit. And of course this plate current is oscillating at the resonant frequency of the crystal, and this part of that, most of that energy gets coupled out inductively through this little coil here, and it goes off to a transmission line, or it may in some cases go off to an antenna. And so, when you're looking at this thing here, this capacitor right here, this tube right here, let's start at the beginning. This quartz crystal here would be the quartz crystal sitting here right in the front of this oscillator that looks like this, you know, this little guy that's there going around out there. And then the next thing you'll see is, looking in the back, there's a tube here. In fact, you can set that up now and show the transmitter if you don't mind putting the camera on the transmitter. Can you do that?
He is switching over.
Oh, okay. Once sit on the table and then we'll won't be jittering around quite so much. Alright, so now we got our little transmitter there, and this thing here in the front is the crystal, and that crystal is across a grid of this tube here, and the output of that tube is to this coil right here, and that coil has across it a variable capacitor that's under the chassis right here. And that tuned circuit, this coil, this capacitor, is coupled to the grids of these two 807s that are in parallel. So both grids are connected together, both plates are connected together, and that signal is driving these two 807s here. Now these tubes over here that are glowing, they're just voltage regulators, and they stabilize the voltage on the oscillator, and they stabilize what's called a screen voltage in the 807s to stabilize the transmitter so there's no chirp on the signal when I send code. And then you get over here, these plate caps are connected to this capacitor. One end of the capacitor, the other end of the capacitor goes to ground. It's in a box here, so you can't see it, but you can visualize it, sort of. And across that capacitor is this coil. The output of that coil goes to a coax connector, and it goes to the over here to the SWR bridge. And then we've got our telegraph tree plugged in the front, and it's hooked into the cathode circuit of that amplifier tube, as was shown up there. If you could switch back over to that circuit real fast. I'll wave my wand over here, but you can look at the picture up here. Anyway, I'm standing in somebody's way too. So this tube right here, this little dark guy, that's the oscillator tube right here. There's the crystal right there. And then this knob right here is this variable capacitor here. It's a series of plates that mesh and unmesh like this. That's how you adjust the capacity. And then here's that this coil right here is right here in the front. And it's driving these two tubes, the grids in these tubes, which is right here. And the plates of these tubes, the structure on the outside, and we'll get a close-up shot here in a minute of the plates, is connected to the top of this capacitor right here. It has a coil across it right here, like that. Then it goes out through this piece of coax here, goes over to the antenna coupler. From there it goes, or the SWR bridge. From there it goes to the antenna coupler. And so this little circuit here is a boiled down version of that, and you can kind of see what's going on. Now the one thing you notice, there aren't any meters on here. Well, meters are kind of scarce, and a lot of the equipment I built didn't have meters on it. I used other ways to make measurements. And one of the ways I made a measurement for how strong the carrier, how well the transmitter is tuned was like this. Let's see here. See, we got, what happened here? Come on. Let's see. Okay. Okay. So now we got our antenna coupler tuned, but if I come over here, I've got a couple, where is it? Here it is. Here's a 2 turns of a coil, 2-turn coil, with a light bulb across it, that's all it is. And if you hold it here, you can see it samples the energy in this coil. And if I set it here and adjust the capacitor, I can peak this amount of energy in the circuit by watching the light bulb get brighter dim. Another way to do that, and it'll work down here the same way. And I can actually, let me get on the side here. I can actually peak the light bulb. Now that's a maximum for the light bulb. The load is a tiny bit off. So I'm going to peak it for the bulb, the fluorescent tube, because that represents the voltage on the antenna. And so that's another way you can tune these things for brilliance, for maximum. Well, if you had a meter in the circuit, what would that be? That would be the farthest over the needle went off from 0, right? And the needle would go like this. And in the end of this demonstration, I'll swap transmitters, put a little one in there, and I can put a meter in the plate circuit and show you how that works. But anyway, that's how you do that. Now, the purpose of this talk was to talk about peaking the grid and dipping the final. Okay, that's where we're going, really. Well, that plate current in the final that you're dipping, if you didn't have that and you had a light bulb instead, when you dip the final, that's when the light bulb gets the brightest. Uh-oh.
I
Yeah.
didn't understand
I
anything
scared the hell out of myself there. But anyway, when the light bulb is the brightest, that would correspond to the lowest plate current, because when a parallel tuned circuit is resonant, that's when the impedance across that circuit is the highest. And when the impedance is high, the current's low. And when it's off resonance, the impedance is low, so the current's high. And so actually the output and the current go in opposite directions. Now, to be honest with you, when you load up the antenna, you increase the plate current because you're drawing more power out of the transmitter, but you're still dipping the plate current to find the resonance of this tank circuit. If you operate off resonance in an amplifier, off resonance condition is converting a lot of the energy into heat, and the tubes get really hot. You can actually burn them up if they're off resonance for very long. So that's another thing you want to consider with these vacuum tube amplifiers that most of you are still using, is that you want to keep that plate circuit tuned, okay? You want to know how to tune that plate circuit so you can get maximum output and minimum plate current. All right, now the other half of the talk was about peaking the grid, right? Okay, well here's the grid over here, and if it doesn't have as much effect, but when I peak the grid current, you can see the output going up. And so in this little transmitter here, we've got, we're peaking the grid current over here, we're peaking the plate current over here with this control here. And that peaks grid current, this dips the final, like that. And that's kind of the story on that. And you know, now another one thing I wanted to show you while I had the opportunity, if he had his, could show, get up closer with his, computer.
Ed,
Sir? We need a close-up picture here.
Uh-oh,
Can you do that?
I think I have that skill.
All right, now, can you get kind of close to that meter there? Aha, yeah. Okay, we're gonna turn this on like this, okay? Now, and you'll notice when I peak the plate current, the meter goes up, right? All right. Now that's the power going through the SWR bridge. Now, actually, if I turn this over here, all right. Now, so here's the power like that. I put it over here. That's the SWR. It looks pretty high, doesn't it? Okay, but I wanted to show you something that happened. Oh, keep on me.
Okay.
When I adjust the antenna coupler and I get it down to proper adjustment, look at that. SWR went down to 1 to 1. And so when you adjust your antenna coupler, even a simple one like this one, you can adjust it very accurately with an SWR bridge. And if I flip over, look at the power is still the same as it was. And so that's what you're doing with the SWR bridge, is you're looking at the match between the output of the transmitter and the antenna, and you're correcting that match to 1 to 1 with the antenna coupler. In this particular case, it's a very simple antenna coupler. In fact, you could build and use antenna couplers like that today. You know, there's a little project for yourself you could build for if you want to use. Now, this antenna coupler is for an in-fed long wire, and this tube here is simulating an in-fed long wire. That's what it is. And I'd have to make just a tiny little change in this coupler, and it would match to like 300 ohm or 400 ohm open feeder line, and for like an antenna fed with open feeder line. Or I can make another little change to it, and all of a sudden it'll match coax to coax. But very simple little antenna coupler, just a coil and a capacitor across it. It's got a little coil in the front here, and that little coil in the front is called the link coil, and it couples energy. See, there's a link on this one here, this link here couples the energy out of this coil, and it goes through the coax, through the SWR bridge, to this little link right here, and it gets coupled into this coil inductively, and it's a resonant circuit oscillating, and the voltage is being coupled to the end of that antenna, and it's going out as a signal off the antenna. So that's the story on how that's playing. And this is all pretty simple stuff if you look at it from the right point of view. And you know, you don't have to be a rocket scientist to learn electronics, I'll tell you that. It's not that hard to learn. There aren't that many parts, for one thing. You got resistors, capacitors, inductors, coils, you know. You can count them on your hands, all the components in electronics. And you can count with all your fingers, so you ought to be able to count 10 parts. Anyway, so that's the story on that. And like I say, we can peak the meter here.
So if that was a 530, a Kenwood 530.
Pardon?
If that was a Kenwood 530, your process still stays the same.
It's the same. It's the same. Unless it's an automatic rig and an automatic antenna tuner, you're going through the very same process I'm going through here. And in fact, the final amplifier in if you got a power amplifier, the tubes in the plate circuit are identical to what's here. There's no difference at all. There's been almost no change in that theory in 50 years. And then over here, we can see the effect of peak in the grid, right there. Peak in the grid, and when we dip the final, you don't see the dip in the final, but you will in a minute when you change transmitters. What they're doing there, we're peaking the output, but it's dipping the current in the final. Anyway, so that's that half of the, that's that half. Now, what I'm doing now is I would be measuring the frequency. If this was calibrated in frequency, which of course it is.
To the nearest one wavelength?
Yeah. Pardon?
To the nearest one wavelength?
I'm sorry.
To the nearest wavelength?
Yeah.
Yeah, so
Yeah.
you're within plus or minus 40 megahertz?
Oh, probably, you can calibrate this thing. Well, I'll give you a hint, okay? On this particular meter, the edge of my fingernail is 7 megacycles. The edge of my other fingernail is 7.3. So the band is almost a quarter of an inch wide. But, you know, I could build a meter, and this whole thing would be the first 100 kilocycles or first 50 kilocycles, you know. But I use these things because lots of times you get an oscillation going through the thing that's not in the handband. Well, where is it? You know it's there because you can detect it with a fluorescent tube. So you use these wave meters to find parasitic oscillations. Oscillations you don't want. They could be anywhere. They can be clear up on 2 meters. And so that's kind of the story on that whole thing. Now, if you're done gazing for inspiration here, I'm going to turn part of this off and tear part of it down. And I want to put this other little transmitter in here. And the fact of the matter is, while I'm tearing down, here it is. A 1-tube, 15-watt transmitter using the Jones push-pull oscillator circuit from 1925. Only it's kind of modern made. And anyway, in this, what we've got here is, show me that first diagram again.
He's over there.
Over there, Ben.
Faster, Mark, faster. Wireless part of the wireless.
Okay. This is this circuit. This is basically this much right here hooked to an antenna. That's all it is. It's an oscillator, no amplifier. And that's basically what this is, except this is a push-pull oscillator, and there are 2 tubes. There's another tube down here, upside down, hooked to the other side of the crystal, and hooked to the other side of this tuned circuit, and push-pull. But that's what this little guy is here. That's all it is. This was a 1-day project, by the way. And so real fast here, I'm going to tear some stuff down, and I'll plug this other little guy in, and I want to show you what I promised to show you was dipping the plate, okay? And that's what we're going to do. If I can get this screw up here. Can you see that better than I can?
What are we doing here?
I'm losing these 2 screws. I don't have my glasses on, that's the problem. Oh, yeah, that was it. Okay. Okay. Let's see here. There we go. Okay. Now, let's get this guy down here. Yeah. Yeah. I'm gonna take this guy. Now, I'm gonna cheat. I've got a meter, and instead of plugging in the power supply, I'll put a meter between it and the power supply. And I'm done with that. Thank you. Okay. Now, get this guy plugged in here. This guy back over here. Now, one of the things I do, you notice there are two connectors on the back, and I got this double pole switch here. One side turns on the B+, the other side switches the antenna from the transmitter to the receiver. So my TR's right in here. It's just a switch. Works fine. And I do that on a lot of my rig set. One down on the floor is the same way. And it gets me off having to use a TR relay and all that good stuff. Okay. We're ready to go here. All right. Now, let's see here. Oh, okay. Oh, look what you're doing. How clever.
Yeah.
Yeah, oh man. Look at that. Oh, wow. Let's see.
Quote of the week,
Here.
Gary. T-shirt.
Let's see here.
Yeah, this knob here won't work. Gary.
Oh, wait a minute here. Let's see here. What happened to our... What do we do? Okay,
You have to keep down.
yeah. Let's see here. What was doing?
Does this thing automatically ID?
No, it doesn't. It just sits there like a... Let's see here. Well, I guess we don't have enough soup to, make the, I don't know, let's see, what I do with my little,
What are you looking for, Conrad?
oh, I'm looking for my weight meter. Let's see here.
I didn't sleep too good last night.
Huh,
Get your D+ switch on.
yeah. Tell you what, let's stop here. I'm gonna pull this out here.
Double
I think
pull.
this thing will work.
Your double,
You know, it's funny, you can always make things work at home, and the man, they don't work. I wonder why that is.
your switch on the right-hand side of that transmitter
It's off.
is off. The switch is off.
Does this need to be on?
You know that might make a difference.
You got a thing? The cheap seats come in handy one more time.
Okay. Well, let's see what's going on over here.
Hey!
You know, I never been able to figure out why it is when you turn things on, they work. It's a miracle. Anyway, this bulb is a little too big. Let's see here. There we go. Okay, there's that one. And we can, finally got things working here. Now you notice if I tune one direction, it kills the oscillation. So you tune right up to the brilliant part, and then that's as far as you can go. Now we see here, let's try putting that meter back in, see what happens this time. Okay.
So, there you go.
Hey!
Let's see. Now oscillators tune kind of funny sometimes because they don't necessarily always give you a dip because they're going across resonance, but anyway, hopefully you can see the effect here on this meter.
Meter, good, adjust it again.
Yeah, let me, there it is, okay. Now, unfortunately with this Jones oscillator, maximum current on the plate is also maximum output. This is a poor choice there. I'm not able to demonstrate that right. But anyway, that's the one tube oscillator. And you know what you might do, Phil? Come over and light off your receiver and tune the gain way down. And let these folks hear, oh, here's your,
Why do I feel like I'm on the Titanic?
Because you are.
here's your Boy Scout knife there too, if I forget it.
Shouldn't need that.
This one is on 7027. I'll hold the key down so you can find it. Seven zero two seven.
Are you an eighth of an inch off?
Pardon?
Are you an eighth of an inch off?
No, I'm right on. Are you all right, Ben?
Yeah, I'm not seeing it. Yeah.
Then it's gotta be there, because it's showing up on my, wave meter here.
Light bulb's blinking. There you go.
Find it?
Check that.
Oh, what happened to it? Where'd it go?
There they go.
Let me try it, Phil, real fast here. Oh, clear down. Here's where's 70?
7027. Right there. Jiggle back.
We didn't jiggle it.
Yeah, turn that all the way down. Let's turn this off. Not good.
Okay, you may have cooked.
Okay. You had it there. Oh, pull the antenna off.
We're all right.
Hold on here. Now let's do. There it is.
Is it still a T?
Nice and chirpy. You don't really chirp there.
Anyway.
What's that beef in
sorry,
our
Anyway, there it is.
I wish I had a picture.
That's this restriction.
Yes, that's right. We do. Yes, sir.
Anybody have any questions while we got it all together?
What's that?
What I wanted to say about this receiver, back before we had hand clubs, we had Elmers. My Elmer was a mobile telephone repairman with AT&T. And he told me, he said, you should build your own transmitter, but buy a good receiver. And he loaned me a transmitter that looked just like that one down there.
Yeah.
And I had this thing called a grid dip oscillator, or a grid dip meter. Some of you know what grid dip meters were. And a grid dip meter was basically that wave meter that Conrad had right there. It was nothing but a coil capacitor and a meter. You hold a wave meter up and you could tune your transmitter and tell when it was working. So I had to buy a receiver. So my dad bought me this one in 1961. I was 12 years old. And I've had it ever since. It's an old Drake 2D receiver. And it's been a good receiver. It still works. And it sounds as good as the new Crystal receivers.
Or,
You make your own clothing?
yeah.
Okay.
The old receiver, this old receiver was hand band only. It did not have general coverage band. And the other thing about these, this one's kind of a throwback. Conrad, can you make the transmitter work again? Or did you unplug it already?
No, it's
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 gone.
floating around here.
Gone. You disconnected it.
Floating. Can I get the transmitter back just for a minute?
What are these things here, Phil?
This thing is a throwback to the old tuned radio frequency, or TRF receivers. It had a main tuning dial that you tuned for the frequency, but then up front it had what we call a pre-selector dial, which is a tuned circuit, I'll call it a capacitor, that you would tune to improve the selectivity of the receiver. Conrad can turn it on and make it work again.
Yeah, hold on.
That switch right there, there you go.
Now just key it down and hold it. Watch the meter. Get around front of it.
Rogers.
There. Now just key it down.
Phil,
You want the key down?
I want the key down.
Key down. Oh, your gain is turned back.
yeah.
And this is better than transistors, right?
You can hear it down tuned to the 40 meter band. And when you get it tuned on frequency, the signal goes up.
Yeah.
And that's all you did. You tuned the pre-selector, and then you tuned the main tuning dial here. You can see the main tuning dial is set on 7.0 plus 1, 2 and a half, 7.025.
So that's a 16.
And that's about as close as you could get on frequency. You want a different CW tone? You tune a different frequency. You like a high-pitched tone? You did that. Or a low-pitched tone? You did that. And these were all tube type. They had to warm up and stabilize.
What model Drake is that?
What's the
Model 2B,
Oh, okay.
2 Bravo. That's it.
Yep. You done?
Questions?
Questions?
First transmitter, ten tank,
Now, where was this?
506 or something like that. Just a plate and grid. Great transceiver. Great transceiver.
Conrad,
Yeah.
why don't you
I
explain,
gave it away for $50.
when you were designing the circuit, how you decided what tubes to use?
I got my general license.
What should I use?
My wife made
What tube? How do you decide what tube?
Why?
Tubes?
Yeah.
Oh, well, I wanted to build transmitters using all the different tubes, just to see what they were like. So I built hundreds of transmitters over the years, and I built transmitters for almost all of the tubes that were ever used by ham radio operators for transmitters or
25
used by companies to build amateur radio equipment. So I've used all the tubes, and in a lot of cases, like that little transmitter's going around, that it uses a 6N7, which is a dual triode. And I decided I'd never built, the 6N7 is a popular tube used in Jones oscillators back in the late 30s, 1935. And so I decided to build that little transmitter to see how a 6N7 worked, and it works really well, as you can tell, you know. And so I built, you know, all the tubes, 2E26s, 6140s, 807s, 1625s, 837s, you know, 4-400s, 4-250s, you know, all the tubes, so. And a lot of my equipment I build, it kind of piles up, so I sell it on the eBay, and I buy some more parts and build some more, so. You have a question?
If there is a cathode current, does that not make the key, metal parts of the key hot?
Yeah,
Okay, so if you're transmitting, hit the metal part of the key,
if you put your finger across it, it gets zapped.
yeah.
But, you know, there's other ways to key, you use grid block, or even then there's a little voltage on it, but, you know, you can, there are circuits you can. Another way to key transmitters is to key the screen voltage, and that works really well. And there's sometimes, I build transmitters that key the screen voltage, you know, and then ordinarily people don't do that, but it works fine.
Oh, is that him?
You can key the plate voltage, actually, you know.
Yeah, since we moved on up here.
Are there any other quick questions, or
Yeah.
anybody, everybody on overload? Well, I'll be tearing stuff down here.